Hello, EC3 participants. Thank you very much for attending this section and listening to my conference presentation videos. I really apologize that I couldn't attend in person. I hope you enjoy the beautiful weather there in Greek. And before I start, I want to show my appreciation to EC3 organizations. Thank you very much for your input to give us this opportunity to present. Also, I want to say thank you to my co-authors, Adole, my students, and Chen, the professor who is going to join University of British Columbia, and also Dr. Borja, who is a professor in New University of Dhabi. So today, my topic is investigating energy saving when using IoT devices in buildings, a case study in the UK. So this is a small case study we did together just to initiate our collaborations. I'm going to show you this quick case study in 4 parts: background, methodology, some results, and conclusion. First of all, let's talk about the background. As we all know, globally, we are trying to target the carbon reduction emissions, for example, 2030 goal, 2050 goals, or reach carbon neutral in 2060, 2050. In order to achieve that, we do need to work on efficiently or dramatically to reduce the emissions from every sectors, and the construction sector does have is a big contributor to carbon emissions. For example, on the right side of the figure, you can see information from IES that 38% of the emissions are from the construction sector, directly or indirectly. So we have a lot of work to do in order to push the construction industry into carbon neutral. So there are many solutions being proposed in the industry to reduce carbon emissions. For example, different type of building design, building systems, and smart building is one of the effective options to reduce carbon emissions by reducing the energy usage in the operational stage. How to achieve that? I think we all know that just by applying system automations and passive controls through different technologies, by using sensors or big data assessment to analysis control the building performance when the occurrences are related. And IoT, or full name Internet of Things, are the main one that have been integrated with buildings to be called smart buildings. So IoTs have been researched for many years, and there are approved studies that IoT can reduce energy usage during operational stage through different ways. For example, as shown here, adjust the HVAC system and reducing the light and equipment usage, because IoT has the sensors to control the lighting and can optimize the HVAC system usage. Also, IoT can detect occupant activities and optimize based on the user behaviors. On the other hand, IoT does have some concerns on environmental impact, as we all know that everything we use or produce or manufacture does have an embodied impact, because we need to manufacture it. We need raw materials, manufacturing equipment, and energy. So this is a drawback of applying IoT. Also, at the end of the lifespan of IoT, there's new ways that we need to deal with. The usage of IoT getting popular during the building sector, there are many more new ways coming out every year. How to deal with this will be another concern which needs to be added up into the building carbon emissions. And also the IoT is not only just the sensors. There are many and other accessories. We need to ensure the batteries, ensure the wire systems and the insulation systems, all etc. has to be linked with IoT. So this could be another additional impact into the building carbon emissions. So comparing these two differences, the energy saving as well as the life cycle impact, we need to think about, are this IoT really a good approach throughout in the building life cycle? So which come up with this our research question: is IoT in smart buildings really saving energy and reducing carbon emissions? Or IoT can save energy during operational stage. Is this energy savings can outperform the embodied carbon emissions? So, in order to answer these questions, here we come to this research objective: to analyze the embodied emissions from IoT devices versus emission reduction from building energy usage due to IoT operations. So, in order to analyze the difference between the embodied emission with the operational emission reduction and the embodied emission increase, we come up with the following methodologies. Okay, so methodology section. So since we all know, even though digital twin is getting very popular, but this is not easy to find a physical or practical building to do analysis. So in this study, we start with simulation tools, and also in the future studies, we're going to apply the theories into actual buildings. For this conference study, we use simulation tools to adopt with different building designs in order to compare the differences before and after IoT installation. So the main tools for simulation is IES VE tool, which can be used to monitor the HVAC system and lighting system automation through or can say by replacing the IoT. So in detail, how did we conduct that? Well, for example, there are three main technology adoptions. For example, we use SoundCast and SoundPath for solar analysis, which was embedded in IES. And also we use Apache HVAC system for HVAC thermal comfort automation control. And then we also use Radiance and FluxDL for lighting and sensoring settings. So just these three technologies were applied or were simulated in IES tool to replicate the IoT functions. And for building geometry modeling, the IES does have a function which we use the engine of Model IT to create the geometry of the buildings to conduct the simulations. And then after we have the simulation conducted, we discuss use life cycle analysis for environmental impact in between the operational and embodied sectors. So, and one-click LCA is the software we use to analyze the actual emissions. So here are some more details. For example, the scenario development, because we want to see how the IoT will impact energy and carbon emissions. So we design the building into 4 scenarios. And the right side is a building investigated in this conference paper. So the commercial building model is the first model we design, and after we have the commercial model developed, we implement a daylight harvesting model by using techniques mentioned in the previous slide to measure if we apply the IoT in smart lighting, how much energy or carbon emission change. And the third scenario is Apache HVAC model, which means we apply the smart HVAC system into the building to measure how much energy can be saved if we apply smart technologies into the buildings. And the last version is a smart building model, which includes all the smart technologies from the previous two scenarios. And Table 2 does mention the design parameters for the investment system in comparison to the conventional building models. You can see for the boilers, in the conventional system, we just use Apache system and to monitor the boiler system, and in the smart building system, we use Apache HVAC system with sensors to monitor the boiler loads. Same for chillers. And for lighting gain, we use between a non-dimming system with dimming system sensors between conventional and smart buildings. So these are the differences between commercial buildings and smart buildings. After we have that set up, and we run the energy simulations through the IES VE software, and then we come up with some results. Now I want to share you some of the results we find. You can see here, these are the three comparable results among the four scenarios. The first figure on the left side, you can see we compare the daylight, the energy savings because of daylight harvesting between commercial building with the smart daylight harvesting building design. So you can see here, like the energy savings by only doing lighting harvesting doesn't reduce too much of energy usage. However, during the summer season in the UK, for example, June, July, August, there are quite obvious energy savings if we do lighting harvest. In opposite way, in December, January, and February, when there's not much sunlight happening in the UK, the daylight saving model does consume more energy than the conventional buildings. So in average, by doing daylight harvesting, we have a 3% energy saved comparing to conventional buildings. On the second figure, you can see that we compare the conventional building with the smart HVAC system implemented. You can see from each month of the year, no matter it is a current weather file or the future weather file. Just worth mentioning here, the future weather file was the weather data we collected from the UK government, which was which considered the global warming impacts. So always a little bit higher energy usage than the current weather files. Anyway, so you can see by implementing the smart HVAC system, the Apache HVAC system, we thus create over 50% or over 55% of energy reduction during operational stage in each month, which is a dramatic result. And okay, on the right side of figure 6, you can see we compare the commercial building energy usage with smart building energy usage during the operational stage. So you can see that there are even more energy savings, or more than 58% energy saved each month of the year by comparing the conventional buildings, which means by implementing smart building into energy usage, it does help reduce overall energy usage. So this finding does align with other researchers in other parts of the world. However, this energy usage reduction has been approved. How about the carbon emissions? Let's take a look at this part. So in terms of carbon emission reduction during the operational stage, it has a similar performance as energy usage. You can see on the left side of figure 7, the annual operational emissions between smart and conventional buildings. The results show that there are over 65% of energy operational emission reductions if we implement smart technologies or IoTs into buildings, which is a good sign. And on the right side, table 3 does show the CO2 emissions between smart buildings and conventional buildings from different aspects, including electricity use, and external walls, fuel usage, windows, and doors, which includes the embodied carbon as well as operational carbon. Okay, so you can see here most of the embodied carbon are the same, except the fuel usage is operational carbon. The smart building does have a reduction of fuel usage. However, for external walls and facade, the commercial building also has a higher emission than the smart buildings. And for sure, this one, if we consider the embodied carbon of the IoT system, that does have a change to the building components. So that's the one thing we measure in this study. So basically, these are some findings we have from these studies. Now let's come to the conclusion and recommendations. We can see that total energy usage density of smart buildings does have a is 135 kilowatt per hour per square meter, 38% less than commercial buildings, and energy savings from artificial light sensors and HVAC sensors are the main contributors to the reductions. And the embodied carbon emissions from smart buildings are at a 7% increase comparing to commercial buildings because of IoT systems. So this is a big thing we should pay attention. And also energy savings from embodied IoT sensors outperform the emission level. So this is the final result, that installing IoT does have overall life cycle emission reductions. So in the future, we were going to spend more time on the real-time monitoring, measurement, and digital twin analysis, as well as lifestyle performance by installing IoT systems in real residential or commercial buildings. And thank you very much for your time and to listen to these videos, and I hope you enjoyed. And if you have any questions, please feel free to contact either of us, myself, Chen, or Borja. Thank you very much for your time. Hope to see you soon in the coming EC3 conferences in the following years.